We continue with non-homogeneous second-order linear ODEs with constant coefficients. So, before we were solving this with the 0 here, we saw the characteristic equation method for solving this type of equation, where we have a second-order linear ODE with the 0 here, and these are constant coefficients, so they are real numbers. Okay, when we have a function g that is not necessarily 0, what we can do, what we must do, is to find the homogeneous solution and a particular solution, and then we have that the general solution of this equation is just putting them together, adding them together. So the solution will be the homogeneous one plus a particular one. So before we already know, we already saw how to find this homogeneous solution. Okay, one technique is this characteristic equation method. Okay, then how to find the particular solution? Now, to obtain the particular solution, we have a method which is the method of undetermined coefficients. And this method is as follows. We try a solution similar as g, the function g. So we go here, look at c deeply and say like, okay, I want a particular solution, and I will propose a particular solution which is similar to this function g. For example, if g is the cosine of px, we would try this combination of cosine px, sine px. Again, some Spanish, sorry for that. Here, sine. Okay. So, if she has this form, a good candidate for a particular solution is this combination about cosine and sine, and these are the coefficients a and b that we have to determine. That's why the method is called undetermined coefficients. So I look at the function g, I propose something similar, and the coefficients part appears here, where, okay, I propose something similar, but I'm not sure if I only take this cosine, maybe it's not the solution. So I have to include a variable there. So the variable the variables will be these coefficients. Okay, so if the function g is a polynomial of order 2, then a good candidate is a polynomial of order 2, where we have to find this e, b, and c. Okay, so hopefully with examples and exercises, you will get used to find these candidates. Once we have the candidate, we find the coefficients by plugging the candidate in the equation, in this case, this second order linear equation. And if we have an initial value problem, which is the equation plus these initial conditions. So in general, if I have equation of order 2, then I have 2 conditions. If I have equation of order 1, then I have 1 condition. And if I have equation of order 3, then I have 3 conditions, and so on and so on. Okay, so we use the initial conditions here to determine the constants that appear in the homogeneous part. So hopefully with example we can fix these ideas about this method of undetermined coefficients and about how to solve an initial value problem. Okay, so let's jump into the example. Here we have a second order linear ODE, non-homogeneous, and we have these initial conditions. Okay, so we just said that to find a solution, a general solution for this equation, we need two things: the homogeneous one and a particular solution. Okay, so the homogeneous one, we saw that we have the characteristic equations method. So in this case, we have to solve this homogeneous equation that has this characteristic equation that we can factorize, and we get these two solutions, two roots, 1 and 2. So they are two real different roots of the characteristic equation that gives these two functions as solution, ex and e2x. So we know that any linear combination of these two is the general solution in the homogeneous case. So we have already this part. Particular solution. For the particular solution, we just saw that we can use the method of undetermined coefficients. So how do we do that? We look at G, and we need to propose something similar to G. G is a polynomial of order 3. So a good candidate is a polynomial of order 3, where we don't know A, B, C, and D. But that's not a problem. We will know them once we plug this candidate into the equation. Okay, so this is our candidate of a particular solution, and we are using the method of undetermined coefficients. So we plug this particular function in the equation. This is the equation. Computing, we are not going to compute this now, but computing the derivatives from the function, we get this new polynomial. 2ax to the power 3 plus blah blah blah, all these numbers here. And now what we want is that this expression has to be equal to our function g, that is x to the power 3. So we force this identity, and for this identity to be true, we need that this 2a has to be this one that appears in front of this x to the power 3. So here is the first equation. Then we have 0 here. There is nothing more in this size of the identity. So this number, this number, this number have to be 0. And that's what we have here, these equations. Then again, computing, we get the value of A, B, C, and D. That hopefully they are correct. I'm a human being, so you can check if I made some mistake. So now we have this particular solution. Where here we have A, B, C, and D. Okay, so going back to the general solution, we know that the general solution is the homogeneous one plus a particular one. So we have here the homogeneous one and the particular solution. We just copy and paste what we got before. And there is these two constants that we have no idea who they are. So far they are any constant. But don't forget that we are solving this initial value problem with these two initial conditions. And it's not a coincidence that we have two initial conditions and two constants to be determined, this C1 and C2. So going back here, we will determine these two constants with the two initial conditions. Okay, so first initial condition, we just use our expression of u here. This is u. And Okay, making the calculations, we get this equation, and using the other initial condition. So first, make sure you compute the derivative of this function, and then you evaluate in 0, and then you have this equation. And again, we are not going to do the computations here, but then we get C1 is equal to -1 and C2 is equal to 1. You can check if it's correct. And finally, we get the solution of this initial value problem where there are no constants. We already fixed and determined everything. Okay, hopefully it is clear. Otherwise, you can always ask some questions.